Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so the title of this talk is Co-opetition in Network Tasks. Essentially, I want to analyze two domains where people are both competing and cooperating at the same time. So here's a brief outline. I'll start by giving a few examples of what co-opetition is and how you can analyze it from a game theoretic perspective. And then the two domains I'll focus on would be advertising in networks, especially advertising in social networks, and then models of network security. So here's something I grabbed from Groupon, which is an immensely successful company in the, say, recent year or so. Essentially, Groupon allows people to use what they call collective bargaining power. So the way it works is you come to a few companies, and these companies, say go-karting in this example, give you a very, very steep discount. So Groupon would offer you all kinds of deals, like going out for karting with a very, very steep discount. Much cheaper, in this case, a discount of 59%, which is a huge discount. But the catch is there have to be enough people that actually accept this deal. So once you get this invite, you can decide to take it. The transaction only happens if enough people have actually bought the product. So better postpone this. So if enough people have bought the product, in this case, more than 1,000 people have bought this product, then the deal is on. Otherwise, the deal is canceled, and basically no one goes to karting for this price. So the model is fairly simple, but it has been a very, very successful firm in the past year. So how does this negotiation game work? Essentially, they're saying people are using collective bargaining power, collective buying power. But you can think of a fairly simple model. So you have, say, 100 buyers that you need to reach in order for the transaction to go through. And the reward is essentially a very, very big discount. So, for example, a discount of, say, $10. And the total worth of this is if you have these 100 buyers is 10 times 100 or $1,000. Now, in the current model that Groupon has, everybody gets the exact same discount. So it's a steep discount, and everybody gets it if they join the deal. But in real-life negotiations, so suppose I'm an HR manager in some firm, and I want to give my employees a nice go-karting day. And if I have 70 users or 70 people that I can bring into this deal, I may expect a deeper discount. So you can consider one domain where you have 4 companies that have different amounts of employees, and they want to negotiate a good deal. So if you have, say, 25 users, you may not expect as deep a discount as a person that has 70 people, especially if the required quota is 100 buyers. So this is a negotiation process, and I want to go over a few ways of analyzing this. So one common method of analyzing this sort of domain is through transferable utility cooperative games. So in these games, we have a set of agents, A1 to AN, and a coalition is just a subset of these agents. And we have a characteristic function, which is simply a mapping from any subset of these agents to a real value indicating whether they're successful or not, or how successful they are. So in the previous example, we have different coalitions of amounts of users. And a coalition wins if it has enough users beyond the certain quota that we had. So these are simple coalitional games. A team, in the previous example, either wins or loses. So in this example, if we take these two groups together, then together they have 95 users. That's not quite enough to reach this threshold of 100 buyers that we need for the deal to go through. So this is not a successful coalition. On the other hand, if we take these two, the 70 and the 50, then we have over 100 users, and that's enough for the deal to go through. So these are cooperative games, and game theory tries and decide what agreements would form in these settings. So which of these companies would work with the other companies, and how would they share the discount? So these agreements are something called imputations. Basically, it's a vector of payoff. So a payoff to each and every one of the participants, and they sum up to the value of the grand coalition, to the total discount that we have available. So I'll denote the coalition's payoff as P of C, just how much a coalition members earn. Or the big question essentially in the previous domain is, how are they going to share this massive discount of $1,000? Who is going to get the deeper discount? So game theory offers several solutions to this. So a solution concept is basically something that just takes one of these games or one of these tables that says, okay, this team is successful, this team is not successful, and maps it into an imputation, into a reasonable agreement. So here are a few that I think are the most prominent ones that I want to mention. Probably most of you know them. So the first one is the core. The core focuses on stability. It essentially says that we're looking for agreements that are not blocked. An agreement is blocked if a team can achieve something that is better than the current payoff that it's getting. So for every coalition, we want the amount that is given to this coalition to be greater or equal to the value that they can achieve on their own. A slightly different definition is the one that refers to fairness or power, which is the famous Shapley value. So the Shapley value essentially tries and measure how powerful you are in these kind of settings. And it's essentially the average contribution that you have across all possible agent permutations. So most of you probably know the Shapley value, but I'll go over this anyway. The Shapley value, well, there are n factorial different permutations of the agents. So in the previous examples, I can bring in these firms with their amounts of user in any order I like. And at some point, we're going to have enough users. So the point where I have enough users in that permutation is the critical player. And the Shapley value is basically just the average number of average number of permutations in which you're going to be critical, or your probability of being critical in a random permutation. So I run across all different permutations. This expression here simply measures whether adding this extra user actually helps, whether it increases the value or not. So to show you why essentially people will not necessarily share the discount in an equal way or in proportion to the number of the users, I want to give you the following example. So the simplest method we can think of is if I'm bringing 30% of the users, I should get 30% of the discount. But that's not necessarily how it's going to play out in negotiation settings. So if we have one group of 50 users, another group of 26 users, and another group of 26 users, you can see that this big group is almost twice as big as these two small groups. But if the threshold, if the amount for actually going through with the transaction is having 51 users, then you see that neither of these on its own is successful, right? Because even the big one only has 50 users. But any two of them are successful, right? So I can take a big one and a small one. That's enough to make the transaction go through. But even if I take just the two small ones, then that's also enough for it to go through. So in a sense, none of them are more powerful than the others, and that's exactly what this concept measures. So if we take the previous examples, if we have 100 users in total that we need, and these are the group sizes, if we compute the Shapley value in this game, then we see that this group would get, the 25 users group should get 8.33% of the entire discount. The big group would get 41%. And these two smaller groups would get exactly the same, although they don't have the same number of users. So this is how the logic of the Shapley value operates. Now, if I slightly change this example and have this smaller group being of 15 users, then you see it will get none of the discount at all. So what's the reason for this? Well, essentially what happens is as follows. If I have either this big group, adding this 15 users will not be helpful in any way. Because I will still not have enough to go over this threshold. And also if I take these two small ones, then I have 80 users, I add a 15, still not beneficial. Now on the other hand, if I take any two of these groups, then I already have more than the 100 users I need. So essentially this group is never helpful to go over this threshold in any combination.
Sorry, can I ask you?
Yeah.
So in the original, in the example at the beginning, the company is giving this discount. So if there are 1,000 people that subscribe, each of them gets a discount.
Yeah, so the current Groupon model is simplified, right? It says that if I bring enough users, you get the discount.
So that's what's happening in this company.
In Groupon, they do not have a more sophisticated model where they negotiate the discount. So what happens is behind the scenes they negotiate.
They know each other that they subscribe, or I can go there and I see that there are 999 people that subscribe. I subscribe 1,000. I get this money, and then someone comes and say, you should give me some money because I say what you want from me.
Yes. So behind the scenes, currently they're not doing this, but big companies are actually doing this, right?
Okay, so
If you have staff in your company, you could expect you can negotiate a bigger discount. So you could group up a few people together. So I'll mention what Groupon does that is a bit close to this, which is social advertising, but we'll get there. So yeah. Okay, so if we take the other solution concept, the core is actually much more harsh. Here's what the core says. The core says that these groups would get none of the discount at all. That seems extremely harsh. And all the discount would go to this user. So what's the logic behind this notion of the core? Well, essentially, you can never get any discount without these 70 users, right? Even if I pull all these three together, the 15, the 50, and the 30, then all I have is 95, less than 100. So that's not enough to go over this threshold. I will not get any discount. So this group could essentially say, listen, guys, I mean, without us, you're not going to get anything, right? It's enough for this group to grab one of these users and actually achieve something beneficial, but you can't do anything without this big group. So essentially, it's a veto player in this game, and they deserve to get all of the rewards. So this notion is a bit harsh, but it's somewhat realistic in some settings. Essentially, I do believe that they would get a much steeper discount in these kind of settings. Okay, so now back to the advertising models. So there are several models of internet advertising. Probably the most known one is display advertising. So if you go into MSN, then in addition to the content, then you have some display ads. This time promising you fish and chips. A slightly different model is sponsored search advertising, where essentially when you're looking for something in the internet, say car insurance, in addition to these organic search results, then you also get these links. These links are basically advertisements that are being sold in an auction. Now, a slightly different way of advertising, which people have already mentioned today, is advertising through social networks. So imagine that there is a certain product. I may decide that I like it in Facebook, and then one of my friends sees this. They also like this product. One of their friends also likes this product. Eventually, we've got some user that likes this product, but not only likes it, he actually goes ahead and buys this product, right? So these links may be propagating across social networks. So this is just one pass, but in real life, maybe lots and lots of these people would like the product. Essentially, one of these users is going to buy the product. And one big question that we can ask is, okay, how much of this purchase, so suppose this purchase actually generated some revenue to the seller, how much of this amount can we attribute to each and every one of the participants in the network? If there are several paths that lead to the target user, maybe lots and lots of people actually like the product, how do we know which one of them is most in charge or most powerful or most influential in this setting? So just to show you that this actually occurs in real life settings, this is not just a hypothetical example, then here's what happens in Groupon, the same company I mentioned earlier. So essentially what they say is you can earn some additional money, some additional discounts or just cash by recommending some deal to one of your friends. So if you see one of the deals, and you can do this either through Facebook or Twitter, you can just let your friends know, listen, this is a great product, why don't you go ahead? So similar viral features that Sinan has talked of earlier. So it is a real life question, and you can apply the previous solution concepts from game theory to figure out who is to get this extra discount. So this is the exact model of connectivity games. We have a certain graph, which is in this case a social network. We have a certain source and a certain target in the graph. The target is who we want to buy the product. The source is the initial liker of the product. And we can consider a different subset of these agents. So maybe in real life, lots and lots of people actually like the product, but let's focus on one specific group, so one specific coalition. So assuming that we take only these individuals, the question is, would they be able to get the message through to this target user who buys the product? So we can take just these users and the source and the target, keep only the edges that occur within this coalition and connecting the source to the target. So essentially eliminating anything that is not inside the coalition. Then look at this induced graph and ask whether we have connectivity from the source to the target. So in this case, yes, we do have a path from the source to the target using just this coalition. A slightly different example is when we take just these agents to be a coalition. Right? So if we take only these three users, the source and the target, and eliminate anything else, so these other 3 users or 4 users, sorry, are disappearing, then we no longer have a path from the source to the target. So essentially, given the network structure, we have a mapping from any subset of the participants of the network to whether they actually win or lose, whether they actually deliver the message or not. And then we can apply the same solution concepts that I mentioned earlier. So actually, in many cases, we would like a slightly richer model. So for example, we would like to be able to propagate a message to any number of these principal nodes in the network, or these principal users. And some users we may know that are always going to propagate the message or going to send it to all their friends, or essentially these are bought-up people. So these are backbone vertices. So you can think of a similar setting in a network reliability. So you want to make sure that you can deliver a message from any of these nodes, any of the orange nodes, from any one of them to any other one of them. You may always use the back-end computers, but these are the ones that you want to attribute your success to. So here's the formal definition of these connectivity games. Agents are just vertices in a graph. Vertices are either they are either primary vertices or backbone vertices. So backbone vertices are ones that we are always allowed to use. Primary vertices are the ones that we want to connect. So essentially, if one of these users adopts, then we want all the other ones to actually know of the product. And a coalition wins if it connects all the primary vertices using the graph induced by the members of the coalition, the primary vertices, and the backend servers. So essentially, if we eliminate everyone that is not in the coalition, can we still send a message from any one of the primary vertices to the other vertices? So this is a simple extension of the same connectivity games I started off with, having just a single source node, having a target node, and just asking the question, how do we attribute the success of having a user buy the product to the people along the way? So here's one example network I wanted to show you. So imagine these could be other computers or could be people in a social network. Imagine that this user has actually adopted the product, right? Now obviously, suppose all these users also like the product, this user also liked the product, and essentially this guy eventually bought the product. So who do you think is more in charge? Who is more important in actually allowing this guy to get the message and buy the product? No guesses? Which one? What, sorry? One before the target. Yeah, so this one seems much more important. So what is the reason? Well, essentially, this agent is a veto agent. Without this guy, we can never deliver the message from here to here. Right? So obviously, we want to attribute more success to this user. And if we consider the notion of the cores, then this is exactly a veto user. This user actually deserves to get all of the discount or all of the credit in this network. So here's a slightly different network. And again, all these people actually like the product. This guy actually bought it. This is where it started. So again, which one is more important?
All the same.
All the same. Okay, why do you say all the same?
Because both block.
Sorry?
They have the same power to block.
So, okay, so none of them is a veto agent. Yes.
They cannot block.
Right, so it doesn't matter which one of these I eliminate, I would still have a pass. So none of them is a veto agent. That means that the core will not give 100% to any single one of them. Yes?
Are these products that assume no network externalities?
Sorry?
Are these products that assume no network externalities? Because if there are network externalities, then the person up in the upper right-hand corner would be the most valuable because he brings all those others at the top into the adoption, whereas the person at the bottom there only brings the original computer guy in.
So for now, I'm assuming no externalities, but I am attributing success, which is fairly similar, right? So in this example, suppose one of these links fails, right? I still have a certain capability of delivering the message. That's true for any failure. But on the other hand, you can intuitively say, well, this guy seems a bit more important because if I get this guy, for surely I achieve the task, right? So if you look at the Shapley value, what it would say is that this node is actually more important. So here is where the two solution concepts diverge. Okay, so in terms of hotspots, which is what we're looking for in bargaining. So if we're looking for a way of actually doing fair payment in these advertising settings, then power indices, like the Shapley value that I mentioned earlier, would actually reflect the contribution of each member in the network. In terms of a probabilistic assumption, then essentially you can take the following probabilistic model, which is completely equivalent. You can say that the target vertex survives, but other vertices fail with a probability of 1/2. So I'm trying to measure the importance of any single node. I say, well, what happens if this node will propagate the message for sure, will deliver the message for sure, but each and every one of the other vertices will only deliver it with a probability of 1/2. What is the probability of actually delivering the message? So this gives you a certain response. And if you do the same computation for each and every one of the links, then you get exactly the Shapley value. So basically the question is, if I could make sure that one of these users would like the product or pass the message for sure, and each and every one of the other users would only pass it with a probability of 1/2, who would I choose? Who is the one that I would like to guarantee of delivering the message? Now in terms of the core, then it reflects stable agreements. It reflects ways where no coalition would deviate. So in the previous setting, the big problem with applying this solution concept is that it's always empty. It gives no prediction unless there is one veto agent. So there are relaxations of this concept that you can use that do allow you to find more stable agreements than others. So in terms of applying these solution concepts, yes, you can certainly do it, even on real-world network. But there are some computational problems that limits the applicability of this. So for example, if we look at the Shapley value or similar notions that are called power indices, then they're computationally hard. That means that we cannot compute them exactly if the network is large enough. So there are polynomial algorithms, efficient algorithms for restricted networks, for example, trees, but generally we have to rely on certain approximation methods. We cannot compute it exactly. In terms of the core, then again, there is a polynomial algorithm, there is an efficient algorithm for finding it, but as you've seen earlier, it's pretty extreme. Unless there are some nodes that I say are completely blockers, so that without them I cannot actually deliver the message to the right address, then it gives us no prediction. And that relaxation that I mentioned earlier that allows getting away around that is computationally hard as well. Okay, for the second part of the talk, I want to focus on applying similar solution concepts, but to a slightly different domain. So this time I want to talk about network security rather than advertising. So you can think of many, many domains where network security is important, from physical networks where we want to block terror attacks and we're placing checkpoints along various important places. We can think of computer networks where we're protecting servers against attacks. And we can essentially model this as a game where we have different costs for protecting various nodes in the network or various links in the network. And these reflect how easy it is to deploy a checkpoint or examine what's going on in a specific place. And the big question is, what agreements can we reach about allocating these costs? So to give you one concrete example, I want to mention Blue Server, or the Texas Virtual Border Watch. Essentially what's being done in this pilot that has been running in Texas since 2006 is the following thing. There are various cameras that are placed along different places in the Texas borders, and people from the internet from all over the world can take a look at these cameras to see if there's any suspicious activity going on across the borders. Now obviously some places are more prone to say drug trafficking than others. And people can get certain rewards for actually reporting very suspicious activities that leads to the capturing of, say, drugs or any other illegal activity in this area. So this is how their interface actually looks like. You can go through, there's a much bigger list of cameras, obviously. I just chose two specific ones for this example. You can click on this camera and you see the activity, whatever is happening right now, in some place along the Texas border. And you can obviously report any suspicious activity that is going on. So these cameras are not just placed anywhere along the border, but in especially important nodes, in especially important places, for example, junctions of roads, where suspicious activity could be going on. And Texas has managed to capture significant amounts of drugs using this crowdsourcing technology. So how can we, yes?
Out of curiosity, are there penalties for false positives? Like how do they
I'm not sure if they have, yes, you can obviously constantly report suspicious activity. I'm not sure if they are blocking this. Yes. Okay. So here is another model for this sort of a domain. So imagine we've got an adversary, say a drug trafficker, that wants to go from the source to the target nodes. So these could be junctions, and these are roads along that area, right? So again, we want to ask, okay, which places are the most critical ones to observe? So if I have limited resources, I have limited amounts of people that could be watching these cameras, where should I place my cameras? So for example, if I could monitor these exact 3 places, right, and then the adversary can never go through these places. So the effect is essentially eliminating these junctions from the graph, these nodes from the graph. And in this case, the adversary cannot reach from the source to the target, right? So in this case, I've eliminated 3 nodes and I've accomplished my goal. But perhaps I could do it in a more efficient way, right? So for example, I can only watch these 2 specific junctions. And because of this network topology, I can make sure that the adversary cannot reach the target, right? So that's just another one of the examples, right? I can be very, very inefficient. I can still monitor 3 checkpoints, and yet there would still be some way for the adversary to reach the target from the source, right? So the question is, which nodes should I monitor? And again, I want to apply the similar solution concept to decide which places are most important to monitor, or to ask, assuming that we have people observing these places, which places are more important. So a slightly more complex model is where I have different costs of monitoring these areas. Some areas require more monitoring, or more sophisticated cameras, and so on. So if we have a certain price for observing each and every one of these nodes, again, I want to know which ones should I observe. So for example, if I choose these specific nodes, their costs are 1 and 2. For a total cost of 3, I can eliminate all the paths from the source to the target. On the other hand, I may have more sophisticated domains where we have several adversaries that are trying to go from different sources to different targets. So maybe this guy wants to go from this source to this target, and this guy wants to go from this source to a different target here, right? So these domains could be quite elaborate, and it's a hard optimization problem. So essentially, just like in the previous example of advertising that I had earlier, I want to consider coalitions in these network security settings. So obviously, none of these single nodes here is enough to accomplish the goal. But if they cooperate together, then they could do it. So assuming I have a certain reward for, say, finding a drug trafficker in a specific point, how should I share the rewards between the people that have examined the cameras? Should I just give it to the one that captured this adversary, or should I give the rewards between people? Or if we're a team of people, we can decide to watch different subsets of the cameras. We can agree between ourselves how to share these rewards. What agreements would we reach? So again, I'm going to use similar tools from game theory. So the formal model is something I call path disruption games. Essentially, they take the graph structure and they build up a big table mapping any subset of the nodes to a value indicating whether it's a successful one or how successful it is. So these are games that are played on a graph. In the simplest version, basically we have our coalition, a subset of the vertices, and they win if they can block the adversary, all the paths that the adversary has from the source to the target, and otherwise they lose, right? Or in computer science, you call this a vertex ST cut. In a model with cost, then things are slightly more sophisticated. So first of all, I have to understand what's the optimal policy for the coalition. So if we go back to this example with the costs. So suppose my coalition, the people I want to cooperate with, are just these, these 3 nodes, right? So presumably they can block the adversary from reaching the target. But they have different placements of security points. They can place just 1 security point here, and that has a cost of 8. Or they can place 2 security points here and here with a total cost of 4. So out of all the possibilities that achieve the goal, they can choose the optimal policy. And that's the minimal cost for actually achieving the goal. So in this case, they get a reward R if they manage to cut the adversary from the source to the target, minus the amount that they have to pay, the minimal placement of routes. So as in the previous models, yes, you can apply these computational concepts like the Shapley value and the core to actually attribute your success in achieving the task or share the reward in this kind of a domain, but there are some computational limitations. So in terms of even finding just the optimal strategy, the optimal placement, then there is a big difference between a model with a single adversary and a model with many adversaries. So if you have several adversaries with different sources and different targets and they have different costs, then even finding out the optimal policy is a computationally hard problem. So we cannot expect a solution for the game to be easily computable. Even on the simplest models, and just computing the Shapley value, or this notion that I mentioned earlier, is a computationally hard problem. You can only compute it approximately. Whereas for the core, then again, there are tractable algorithms, but basically what they do is locate places where checkpoints have to be placed to achieve the goal. And once you start looking at relaxations or more stable outcomes, then we no longer have computationally tractable ways of allocating the rewards. For specific types of networks, for trees, then again we can find efficient algorithms, but this is a very, very simplified domain. Most networks in the world would not behave this way. So I want to give you a few conclusions. I started by talking about new models of advertising in the internet, social advertising, and I talked about a bit about the Groupon model. I modeled this domain as a certain cooperative game, and said that you could apply various solution concepts to allocate the rewards in a fair way or in a stable way. Then I mentioned a different program, a different domain of network security, where the task on the network is different, but again, could only be achieved by cooperation between the agents. So in this case, I took a different modeling of the domain, but I applied the same solution concepts to come up with reasonable ways of allocating the gains. So in both these examples, solutions like the Shapley value would tell you, given a whole network of people that say like the product, how much of the purchase that this guy made should I attribute to each and every one of the participants, or how they would share the reward for this. And in the network security setting, I've attributed the success of capturing or stopping an adversary, again, to the various nodes in the network. And I've also mentioned several computational barriers that can stop us from actually using these concepts in the real world. Sorry. So in terms of, never mind. In terms of future work, what I wanted to mention is that despite the fact that some of these concepts are hard computationally, there are ways of getting around that problem. So rather than using exact solutions, we can use approximate solutions, and they may not be the completely fair way, but they would be as close as we want them to in terms of the running time. So thank you.